Hey everybody, Thomas here, and welcome to the last episode of this NEO Python tutorial video. So, as I said last time, we are concluding today our NEO project by adding the telescope properties and settings to, well, get a very, I would say, more sophisticated understanding and model on how to detect NEOs as seen from Earth. And as a small recap, well, what did we do and what do we need to detect these objects? Well, we need, of course, to compute their state vector, so the state vector of the NEOs, as well as the state vector of the Earth, as seen from the Sun, so that we can compute the state vector of the NEOs as seen from Earth in the night sky. And well, based on the angles and distances and so on, we computed the apparent magnitude of these objects. So an astronomy parameter that is being used to describe the brightness of an object. And well, the apparent magnitude needs now in this session to be converted into something called the irradiance. So the irradiance is like the watt per square meters. So like the energy rate that is coming to our home planet per a certain area. And well, you will see these values are very, very small. So it's not like kilowatts or something. It's very, very small, tiny values. And this irradiance, the photons of the of the NEO, they are now coming into our telescope. So the telescope consists of mirrors, depending on the type of mirrors, or some lenses. It has a certain geometry, focal length, and so on. But today we will simplify these things, right? So we will just assume it's some kind of telescope and with only 2 or 3 mirrors, and just compute the total collection area of the telescope as well as the reflectance properties of the mirrors. And then the light is being collected into the camera. It's something like a CCD. And we have different CCD properties. We have also some settings, like, for example, the gain or also the exposure time. But today we will just stay with the exposure time as the only parameter we can adjust, so that at the end of the day, we can compute the signal to noise ratio. So we use something like a 16-bit resolution and convert the number of electrons that are being, let's say, kicked out of the light that is being focused on the camera. We convert this to some digital number, and this digital number, the signal, is then converted to a signal to noise ratio, and based on the signal to noise ratio, we can determine how many objects we are able to detect. Now, first of all, let's have a look at some kind of telescope. So you see here something called the Newtonian Schmidt telescope. So I will not go into detail, but you can see here the cross-section of the telescope. Here's the entrance. The light, for example, from a star or NEO is coming into our telescope, coming to some kind of mirror, and then you see here the lights is being focused here, reflected in a mirror, almost at the entrance of the telescope, and then going into, for example, the eyepiece or a CCD camera. So we have like here the mirror size, the mirror size at the back, the mirror size here, so that we have like the irradiance of the object times the effective collecting area, because this area is also obstructed by this one here, times the reflectance of the telescope. And well, yeah, you saw already a spoiler here now on the CCD camera. These are now a little bit, the different pixels we have here. And well, the NEO or star is not really sharp on one pixel. It is more distributed over a lot of pixels, right? So it's like a 2-dimensional Gaussian distribution, depending on, for example, the seeing, so the atmospheric disturbances and so on, also based on the telescope properties. Of course, if the pixels are very, very huge, then of course 100% of the light is being collected into one pixel. But we assume today a resolution of, I would say, 1 arc second per pixel. So 1 arc second corresponds to 1 pixel. And this is, I would say, a value that is quite realistic for an amateur telescope. And well, the light here of the NEO is, the light hits the camera, the CCD camera. The light is, causing some electrons to float freely. Yeah, it depends on the exposure time, so that we have now some free floating electrons that are being read out by some readout electronics. But I will not go into the details of a CCD camera or the readout electronics. Most importantly, it is to know that something I would call now the digital number, so a value between 0 and 65,000, so the maximum value of a 16-bit, is somehow approximately, depending on the exposure time. Yeah, then also the what I call the percentage of light in the center pixel. So we will not integrate over all pixels, but we will just use the center pixel and assume some value here. Yeah, it depends now on the seeing. If the distribution is very broad, then only a small percentage, a fraction is in the center pixel, or a larger one if it's more sharp. Of course, these the distribution can also be here in the center, so it's distributed over 4 pixels, but today we'll just assume the best case, that the maximum is always at the center of a pixel. It also depends on the gain of the camera. We will ignore it today. We will just set it to 1. And then, of course, also depending on the irradiance of our object, and also the what you can say, like the answer function, or the sensitivity of a CCD camera for a certain wavelength or band. So we will use today 550 nanometers, and this corresponds also to a certain quantum efficiency. So quantum efficiency means that, well, if you have, like, let's say, in a very simplified fashion, we have 100 photons hitting our camera, then of course not 100 electrons are being kicked out or are generated, let's say, by 100 photons. It's maybe like only 50 or 80 or 70. So this is like the quantum efficiency, and this ranges for different wavelengths between 0 and 1. And we have different observation bands in astronomy, ranging in our visual spectrum for different bands, and today we will just keep it as simple as possible for 550 nanometers, and that's basically it. So this is this is what we will do today. Now, afterwards, after computing the digital number, we will compute then something called the signal to noise ratio. And the signal to noise ratio is quite simple. You have now the signal here divided by the square root of our contributors. We will simply use the signal itself, and later in the Outlook, if you want to extend the project a little bit and the notebooks, you can work on this part here, but we'll talk about it a little bit later. I would suggest we dive into our scripts, and everything is of course available on GitHub as always. We have here 2 scripts. The one here is called 14_1, and it's basically a copy of 13.1 that generates our enriched NEO model, but it adds code block number 8, where we are converting our apparent magnitude into an irradiance value. So this irradiance here, the function is in photometry.appmag2ir, and this one here is then stored in our auxiliary folder. So here on the left side, photometry, if you open it, you will see at the very bottom the corresponding function and also how it is being computed and what we need for this. But well, let's stay with this here, and we have then at the end our Parquet file that is being called enriched Granvik model with irradiance.parquet. So this is actually also the thing we need now for our script 14.2, where we read in the data in the very beginning. So let's execute the first coding blocks here, where we are reading our data and also compute now the ecliptic longitude coordinates for our matplotlib plot. So the loading takes some time. So here in cell number 4, and now in cell number 5, 6, and 7, we define some functions. First of all, we define the function that is, I would say, telescope optics related. So we have the irradiance times the total area times the reflectance of a telescope. This is, yes, again, it can be way more difficult or more sophisticated, but I would suggest to keep it as simple as possible. And the same here also for our function that I just call watts to signal, where we have the exposure time, the irradiance of our object, where we have something like a dimensionless number that indicates the ratio of the light in the center pixel, And then also what I meant with our band quantum efficiency. So here we will write later 550 nanometers and a quantum efficiency of a certain value. So this is being computed here. So it's simply the function I have shown you on the presentation. But there's one thing that's very important for CCD cameras, because we shouldn't simplify things too much, because CCD camera has a linear and a non-linear region. So of course we have we create some electrons, free floating electrons in our CCD pixels, but at some point we get to a point of saturation, and the closer we reach the saturation, the more the function deviates from a linear function and, well, approximates to some kind of constant. So we have to be very careful. We simplify this here with a linear function, and we say, okay, if we reach this 16-bit maximum resolution, we simply set it to the maximum resolution. Yeah, so I know there are more sophisticated functions than this, but I think it gives you a good introduction into this topic. So let's execute this one here. And then at the end, also the signal to noise ratio. Again, very, very simplified. I will talk about it later, what we can add in the future. Now I would say, let's create some telescope settings and CCD settings. So here in cell number 8, I just said, okay, I don't know, a small telescope with an effective area of 0.1 square meters. The reflectance is 80%. 25% of the light is in the center pixel, and this here 550 nanometers is the wavelength for our V band, and we set a quantum efficiency of 50%. So I would say these are amateur telescope values, so it's not very fancy electronics or a telescope. It's everything, I would say, for beginners or even a small advanced telescope. And the observation setting itself here is 60 seconds. So you can vary with these values here and see what happens, how everything is affected. But for the video, we would just put this here and set our default settings. Now we need to convert the irradiance into the watts, the signal to noise ratio in this cell number 9. And at the end, we also determine whether a object has been detected or not. And I would suggest that, well, we set something like a signal to noise ratio of at least 5. So the signal has to be 5 times higher than the noise to be detected, so that that later here afterwards we can then also convert it or filter everything out. So we don't need to filter them by the apparent magnitude. We simply say, okay, if the value reaches a certain signal to noise ratio, we assume it to be detected. So let's execute this cell here. This takes some time, and then I can execute this cell also. Sometimes some errors will spawn because of the square root, but well, this now takes a few moments, and until then, I would say to have a short break, and let's wait for a few seconds. And we are back. Our computation is now executed. So you see here all 4 computations are through, and we also filtered our data. Now, before we check our sky map here in cell number 11, what we can do is we can, for example, check the signal to noise ratio versus the apparent magnitude. And what do we expect? Well, we expect that the signal to noise ratio decreases for fainter objects, and fainter objects means larger apparent magnitude values because it is inverse correlated. So let's see. And what we see here, the apparent magnitude you see here on the x-axis and the signal to noise ratio on the y-axis. And you see here for some cases we have also some kind of saturation. So this is probably the area where our 16-bit maximum filter has been applied. Okay, cool. So I would suggest now in the very last cells, what we do the same thing as the last time. We are executing everything to compute a 2-dimensional Gaussian kernel density estimation. So that's what I want. This is the word I was searching for. We have now in a de-enriched population something like almost 5,000 NEOs. And so we compute here the kernel density estimator. So this takes a few seconds so that afterwards we can now plot also our data in a sky map. So this is the same thing we did last time here in script number 13.2. And this is the same thing we did, but only using the apparent magnitude. So feel free to do some other filtering. Of course, now we simply use the signal to noise ratio of 5 or larger. And this is now, this is now our only filter here, whether it has been detected or not. And small spoiler, our distribution will have the similar appearance as last time. So the computation of the KDE takes a few seconds. Now the plotting routine is being executed, and we see here our sky map. So what we see here, ecliptic coordinates, we see here the sun and also the area where we can't detect anything at all. And then here's the opposition direction. We see that we have most object in the opposition and also here closer to the sun, but everything around the ecliptic plane. So if you're searching, if you want to observe as many objects as possible, you should rely here on the ecliptic plane. But well, if you do some filtering and you would like to find, for example, high eccentric objects or something like that, maybe the distribution looks a little bit different, and then you can adjust your observation strategy accordingly. So, well, this is everything we need now to get a distribution, a detection probability distribution in sky coordinates for our telescope setting. So the question now is, what's next? Well, the equation says it, signal to noise ratio. I will mention it just in a moment. The first thing we can do is we have to consider the neo velocity on the CCD. Because, well, if our exposure time is maybe 60 seconds or a minute or even 10 minutes, depending on the telescope properties and so on, the object itself will move on the CCD. So what happens is that the object has a maximum dwell time on each pixel. So it moves here along and leaves the pixel. And maybe it is so fast that, well, our we will never reach saturation. It will reach some digital number value of, let's say, 10,000. And although our exposure time is way, way longer, the value remains there. So it will not improve further because the neo moved out of the pixel. And what happens then is, well, we have noise effects, thermal noise, background noise, and the noise will add up. And maybe our signal to noise ratio will worsen for certain objects if the exposure time is set too high. So this is something you need maybe to consider, and it's maybe something you can do in a future project. So we have to, can also model the resolution. We can also approximate the Gaussian a little bit. So now we use only the center pixel, but maybe using everything would be quite nice. And also adding all the noise, like the dark noise. We have something called the bias, the readout noise. So every readout adds also a certain noise. We have the background noise of the night sky. And we have also something like the zodiacal light. We have the Gegenschein effects. So all noise sources can be added or should be added to get a more and more sophisticated understanding and overview of this telescope detection modeling. Well, that's all now for today. That's all now for the NEO project. I hope you learned something in this NEO project. I hope you improved also your skills a little bit. Maybe you also improved my notebooks already or found some bugs. Then always reach out to me. Well, the NEO project is now concluded from that side. I will now work on new projects and new tutorials where we will hop back to our, let's say, generic tutorials where we do some more 3D modeling again, so without any project purpose. And I hope you enjoy also the sessions in the future. If you have any comments, if you have anything, then please reach out to me. And also in the meantime, I will change up the setup a little bit for future videos. I will also add maybe some YouTube shorts or so with short coding blogs or something like that, or some ideas. I don't know, maybe something like showing some science facts or also some tools or so in some 1-minute videos to reach out to the people who do not have a lot of time to go through my videos, which take sometimes like 10 to 30 minutes. And also maybe adding some videos set up or so to, so that I don't only have this plain boring screen sharing. Anyway, thanks for listening and see you next time.